once again to Moto Online. Before you, this is teacher Mugulumiza Noah, physics facilitator. Today, we're going to learn about modern physics. Now, before we continue, Global High School is a school that is located in Katabi, in Entebbe municipality, just off 3 kilometers off the Entebbe Kampala Express Highway. So the school is conducive, has a good environment, professional teachers, and all that. So welcome you all. Now going back to our chapter for today, we have modern physics. This is a topic that is studied in senior 4 according to the selected syllabus of the new curriculum. Modern physics. Physics that is modern. Just the word itself, modern physics, just appetizes. It is very much interesting to know what trends in the world, what is current. So we're just going to look at the physics that is modern. You always ask yourself, how do X-rays work? How do people really tell that this bone was broken or not, and which part exactly? You always wonder how people come up with atomic bombs. Russia fighting with Ukraine and all that. They are using physics to fight. And still we can use physics to do so many things as we are going to look at. Now, all those things were not there before in those gone days. But because of the modernity in technology, so we happen to have the modern physics. So it is because of physics that we have so many things that are going on worldwide. Let's look at modern physics. Now, modern physics, the genesis of it just begins with the structure of an atom. So we are first of all going to look at the structure of an atom. This is not chemistry, but physics. So we are just going to look at the structure of an atom, then we see what takes us where. So first of all, an atom itself is the smallest part of an element that can take part in a chemical reaction. You can define it in that way, or someone can opt to define it and say an atom is the smallest electrically indivisible particle of an element that can take part in a chemical reaction. Now, the structure of an atom, it has the nucleus, then it has energy levels on which these electrons keep orbiting like that. So this is our atom. It has this inner part, the central part of it, which is the nucleus. Then around the nucleus, we have energy levels or shells here. These electrons, they keep orbiting around the energy levels or these orbits here. Now, these are electrons that are, we can abbreviate them with E. Then this is the nucleus. Now we have the constraints of an atom or parts of an atom. It has the electrons, then it has the neutrons, and it has the protons. Electrons can be abbreviated with E, then neutrons with N, small n, and protons with P. Now, this atom here plays a very vital role in the modern physics of today and in the future to come, as we are going to see. Important notes to put down after having seen the structure of an atom. We are going to look at some terms. For example, isotopes. Isotopes. The chemistry students, this is not new to you. Isotopes in the plural, but if it is one or singular, then it is an isotope. The definition of it, an isotope, or isotopes, atoms of the same element that have the same number of protons but different mass number. Atoms of the same element but having the same atomic number and different mass number. What do I mean? We have different types of isotopes. For example, examples of isotopes. Examples of isotopes. We have the chlorine isotope, where we have chlorine, which is number 17, the periodic table. The number of protons of chlorine is 17, because proton is the number of protons is also equal to the number of electrons. So you should also note that. So since chlorine is number 17, or it has 17 electrons, that means even the number of protons are also 17. So we have chlorine 17, 35. We also have chlorine 17, 36. We also have chlorine 17, 37. This is an example of an isotope. They have the same number of protons, but different mass numbers. The mass number for this one is 35, 36, 37. They are different, but the number of electrons or protons are the same, 17, 17, 17. So chlorine 1735, chlorine 1736, and chlorine 1737 is a perfect example of an isotope. You can have many more. We can have hydrogen 1, 1. We can have hydrogen 2, 1, 2. Then we can have hydrogen 1, 3. The same number of protons, different mass number. Still, we can have carbon 612, we can have carbon 613, and we can have carbon 614. You also realize that carbon is also an isotope because it has the same number of protons, but different mass numbers. 12, 13, and 14 are different, but 6, 6, 6 are the same. So when you are required to cite out or to give some examples of isotopes, you can have chlorine and you write them. You can have hydrogen, you write, and then you have carbon isotopes. Okay. Now, having looked at some isotopes and their examples, now let's look at another term called atomic number. Atomic number. Atomic number. We can represent it or we can denote it with Z, atomic number. This is also a physics term as well as a chemistry term. Now, atomic number simply refers to the number of protons that are present in the nucleus of an atom. The number of protons in the nucleus of an atom. Remember, our structure, it had the nucleus, which nucleus has the protons and the neutrons. So the number of protons inside this nucleus is termed as atomic number, and we can represent it with Z. So is the number of protons in the nucleus of an atom. Okay. Then another term is atomic mass. Atomic mass. Sometimes you can even call it nucleon mass. Nucleon mass or nucleon number. Now, atomic mass, we can denote it with A. Now, atomic mass, for it is simply the number of protons and neutrons in the nucleus of an atom is the number of protons and neutrons in the nucleus of any atom. So it's different from atomic number. Look here. I always refer to our atomic structure. It has the nucleus, and inside the nucleus, we have constituents in it, or we have subscribers of the nucleus, which are two. We have the neutrons and protons. Now, when we add these neutrons plus the protons, because they are all residing inside the nucleus, we get what we call the atomic mass. And we write them using A, letter A. So we shall denote it with letter A. Now, we are going to look at how we can illustrate an atom with a mass number and then atomic number. Now, if an atom of an element X if we have an atom of element X written like this, capital X like that, then it has the mass number which is put up here, superscript. Then we have the atomic number Z, which is written here. It is a must, it is mandatory for you to write mass number up here and then atomic number here. Having known that atomic number is the number of protons and neutrons in the nucleus of an atom, then protons, atomic number, just the number of protons in the nucleus of an atom. Now, you can note the following just from the definition. So if we need a mass number then is given by the formula is the number of protons, which proton is the same as atomic number. So Z plus the number of neutrons inside the nucleus, so plus our N. Remember, neutrons were denoted by N. So atomic number or atomic mass or nucleon mass is given by the formula atomic mass equals to Z plus N, where Z is atomic number or number of protons, and then N, small n, is the number of neutrons inside the nucleus. Remember, these two were the constants of the nucleus. So when we sum up them, we get what we call the atomic mass. So from this, we can actually get either N or Z. Just it's a matter of making N of your wish the subject. So when you want to get the atomic number or proton number, it is now A minus N. The same applies to N. It is A minus Z when we use some simple mathematics. Now, let's have some examples. Assuming they give us an example and we have given a chloride atom. It is 1735, like that. Then they ask you that find the number of electrons in the atom. This is our chloride atom. It has the atomic number or proton number as 17, and then mass number or nucleon mass or nucleon number as 35. So they want us to find the number of neutrons inside the nucleus. So we shall simply recall our formula. We shall say recall that mass number is equal to proton number or atomic number plus N. So when we make N the subject, we shall have N equals to mass number minus Z. But our mass number is always written up here. So mass number is 35, then less 17. So what you get here gives us the number of neutrons, and these are 18 neutrons as required. Now, that is one of the examples. So in modern physics, as we proceed, we are bound to look at some equations and we balance them. However, we balance these equations using physics principles, not chemistry principles. Now, on that, this brings us to a new term. After having looked at isotopes, atoms of the same element with the same number of protons but different mass number. They may ask you, what causes the difference in the mass number of isotopes? It's simple. You've seen that mass number is protons plus neutrons. Then atomic number is only protons. So now, what is causing the difference? It is only the neutrons. So the difference or the discrepancy in the number or in the mass number, it's just because of the different number of neutrons in different nuclei. Okay. Now, we have a new term called radioactivity. Radioactivity. Radioactivity, just two words joined. Radio and then activity. Radio, that means there are kind of waves, and then activity, it is a disintegration which is continuous. So by definition, radioactivity here, it is the spontaneous. We shall allow ourselves to use these words because they are necessary. They bring out the meanings. Spontaneous disintegration. The spontaneous disintegration of heavy, unstable nuclei to form stable nuclei accompanied by the release of radiations. Now, some atoms are so heavy, and because they are so heavy, they are unstable. If they are unstable, it's like having someone who is, allow me to use, if someone is maybe so big and someone who is small, when these people are to sprint for a distance, it is easy for this smaller one to actually sprint faster than this, because this heavy person is not that stable. Now, some of the nuclei are heavy and unstable. And since they are heavy and unstable, they undergo what we call spontaneous disintegration. They disintegrate to form stable ones. Now, that process is referred to as radioactivity. The spontaneous disintegration of heavy unstable nuclei to form stable nuclei accompanied by the release of radiations. Whenever a heavy unstable nucleus is spontaneously or continuously disintegrated, then it forms a stable one, but with the release of radiations. Now, let us look at the radiations that are released during radioactivity. Radiation is produced during radioactivity. Now, we have basically three radiations that are produced during a spontaneous disintegration. One is alpha particle, and this alpha particle you can denote it with this letter alpha. Then you also have beta particle or beta radiation, beta particle, which is denoted by letter beta. And then we have gamma rays, which are denoted by letter gamma. Now, these radiations, they come as a result of the continuous disintegration of a heavy unstable nucleus. So, in the process of forming a stable one, the heavy nucleus undergoes a spontaneous disintegration and it forms a stable one accompanied by the release of these radiations, alpha, beta, and gamma. Okay, let's briefly look at an alpha particle. Alpha particle. An alpha particle. And it is written like that, alpha. Now, an alpha particle is a helium atom. Is a helium atom. In bracket, we can write helium like that, mass number 4 and atomic number 2, like that. So, whenever they talk of an alpha particle, this shouldn't skip your head. Just know an alpha particle, they are talking about a helium atom of atomic number 2 and mass number 4. That means if a nuclide maybe undergoes a spontaneous disintegration and releases an alpha particle, you should then put this into consideration. Now, during the process of spontaneous or continuous disintegration of a heavy unstable nucleus to form a stable one, if it disintegrates and emits an alpha particle, then in the process, the atom loses mass number 4 and then also loses proton is as 2. Now let us look at an example here and we see how we can deal with these physics equations. However, we have given that a radioactive element, we have this radioactive element. If a radioactive element X, which is written by this Zn, hoping that you still recall Z is atomic number and A is mass number, undergoes under spontaneous disintegration or undergoes decay. If it decays or if it spontaneously or continuously disintegrates, then it forms a stable nuclide, but that nuclide previously was X. That means if you lose something or you gain something, you don't remain the same. So that means if it was X with atomic number Z and mass number A, then it will become a new stable nuclide Y, then plus emission of an alpha particle plus an alpha particle. Then if we are to balance this equation here, one, we have to put this in mind that, okay, alpha particle is a helium atom which has mass number 4 and atomic number 2. So you simply rewrite this and say it was nuclide Z with atomic nuclide X with atomic number Z and mass number A. When it spontaneously disintegrated to emit an alpha particle and it became stable, so it became Y plus alpha particle. But in this same round, we shall write alpha particle as a helium atom of atomic number 2 or proton number 2 and then mass number 4. Now we have to find the number of protons for the new stable nuclide Y, and so is the mass of this new stable nuclide Y. So at the moment I don't know them. I can put here A and I put there letter B. B represents the number of protons of the new stable nuclide and A represents the number, the mass number of the new stable nuclide. Now we shall simply say the right hand side is equal to the left hand side. So I'm just going to sum up the left and equate it to the right. So I'll simply say A, the upper, when I consider the left, the mass number on the left hand side should give me whatever is up on the left. So capital A is equal to small a plus 4. But my intention is to make a, small a, the subject. That means my A is equal to capital A minus 4. The same applies to the proton number or atomic number. So Z is equal to B plus 2. This goes with that, like that. Even the upper ones, they go correspondingly. So my B will now become Z minus 2. This is what I've just explained. That during the disintegration process, for a heavy unstable nucleus, when it is in the fight or it is maneuvering to become stable, then during the process, the mass number will reduce by 4. You are seeing a reduction here. This mass number was the previous nuclide, which was unstable. And so during the process to become Y, which is stable, it is losing 4 here. And then even the atomic number or proton number is also reducing by 2, as we are seeing here. Let's have an example and we see what I'm talking about. We have a radioactive substance, X. It has atomic number 6 and mass number 22. This undergoes decay and emits an alpha particle to nuclide Y. It undergoes decay to form Y and emits an alpha particle. So now they want us to write a balanced equation of the reaction process. Now, this is the heavy unstable nuclide. It is going under spontaneous disintegration to become stable. I've told you that when you lose or gain something, you don't remain the same. So it was previously X and now it is Y, plus emission of these radiations. The radiation is emitted alpha, beta, and gamma. But case in a point, we have only considered the alpha because it's what we've looked at so far. Now, we are just going to say, okay, this is 22, 6 as our heavy unstable nuclide. It is spontaneously undergoing decay to become Y. We shall now put, and I say this is A, this is B, then plus an alpha particle. This alpha particle is a helium atom of mass number 4 and atomic number 2. Well, now let us just put that in consideration and find values of A and B. So we shall say that A is 22 less 4. The mass number reduces by 4 and atomic number reduces by 2. So my A will now become, this is 18, and then similarly, my B will be also reduced by 2. So 6 reduced by 2 here, so my B will become a 4. That means when I rewrite my equation of reaction, or equation of decay, I'll now have X, which had atomic number 6 and mass number 22, undergoing decay to become a stable nuclide Y. With the atomic number now 4, it is stable as reduced, and mass number 18 plus an alpha particle, which is a helium atom of atomic number 2 and mass number 4, like that. However, you should not be confused. Cases in point like a nuclide X undergoes decay to form a new nuclide Y, and it emits 3 alpha particles. Actually, let us have that as our example, so and we see if it emits more than 1 alpha particle, what are we supposed to do? So supposing I have a nuclide X and it is of atomic number 12 and mass number 36. Now it emits 2 alpha particles to become Y. So it is now Y plus 2 alpha particles, like that. So they want me to now write the atomic number of Y and mass number of Y still, or to write a balanced equation. Now, we shall say this was X 1236. When it disintegrated, it became Y with atomic number B and A. These are just letters which you can use your own that you're already familiar with. So plus 2 alpha particles, but these alpha particles, each is a helium atom of atomic number 2 and mass number 4. So I just include or incorporate a bracket, then I put the helium atom. That means inside is 1, but we have 2 alpha particles. That automatically means that these 2 will affect everything. So we shall have now 36, giving us the right hand side, which is A, plus now it is 2 times this 4, which is 8. So you realize that A equals to 36 less 8, and our A becomes 2, 8. Similarly, we have 12 giving us B, plus still this 2 is affecting everything inside the bracket. So it is 2 times 2, which is a 4, and now our B will be equal to 12 less 4, and now our B will be equal to 8. Then you finally write a balanced equation as X 12, 36 undergoes decay to become stable, and it became nuclide Y. With this time round atomic number 8 and then mass number 28, plus or with accompanied by the emission of 2 alpha particles plus 2 alpha particles, which are helium atoms of mass number 4 and atomic number 2. Thank you for listening. I welcome any questions or a comment. In case there's something that you've not properly understood, here is the time submitting your queries here. Meanwhile, I welcome the following. There's my son Chambo Derek. Welcome. Nakauki Fiona, Mwangus Johnson, Nakito Sanya, Elijah, you also welcome. Jessica, Helen, you welcome. Nabatanzi Betty, you welcome. Ruth Nabada, you welcome. Mugisha Kevin, you welcome. Nalunkoma, Ruth, you welcome. Mwangus Johnson, in advance, you also welcome. So, welcoming any questions in case there's something that you've not understood. So basically, this is a senior 4 chapter, and to those in the holiday, mostly the same candidates, the senior 3s, but of course you are now candidates. This is one of the chapters that we'll be looking at. We shall digest more parts of the modern physics and we simplify it. We are here basically to simplify physics for you. Physics is simple. So don't get stuck there. Are the X values constant? Someone is asking, are the X values constant? Now these X values, they will be given to you. Don't mind, they will be given to you. That a nuclide may be X, and then they give you the proton number and then the mass number. Then they say it disintegrated to form a new nuclide Y, whose mass number and atomic number is not given. Then they say plus emission of an alpha particle. But we have, remember, we have only looked at alpha particles, but we have so many particles. We have beta particles and gamma particles. Food for thought, we shall look at these later on. And then we look at a combined equation which will incorporate emission of alpha, beta, and gamma, and then we see how we can solve that. So X values will always be given. When are we having a look at emission of beta particles? Hold on, we shall look at that. Can we get a scenario that topic has? Actually, to precisely refer you to a simple scenario, just a reference in the previous senior 4 end of year assessment by UNED chemistry, because this part cuts across both in physics and in chemistry. That's why you are looking at atoms and all that in physics, and it is also studied in chemistry. And there is a question in chemistry that came where they brought a scenario which happened in the areas in the parts of Nagasaki and some part of Nagasaki in those Western countries. Then they asked, which type of bomb was that? Now, yes, actually it was item 1 in chemistry. So that part here was of course modern physics. Which type of bomb was that? That is atomic bomb. So when we are going to look at the applications of this modern physics, and we shall look at so many different things where we shall see that it is these particles here and other particles like X-rays and all that that are used to make atomic bombs. However, they are not only used to make those dangerous things, they're also of vital use in our day-to-day life. Like when you fall sick and you want to be diagnosed, you always go in hospital and they say they're going to scan you using these X-ray machines. That is an application of modern physics, because X-ray machine uses X-rays, which are these radiations, and so many more. In case don't have any other question, thank you for listening. The alpha particles only produced by unstable helium nuclide. Now, alpha particles are helium atoms, and helium has atomic number 2 and mass number 4. So just quote this, that whenever they say it emits an alpha particle, just know that an alpha particle by definition, it is a helium atom of atomic number 2 and mass number 4. Maybe the something that I've maybe skipped, the properties of alpha particles, briefly in just a second. Properties of alpha particles. Properties of these alpha particles. Properties of alpha particles. One, these alpha particles, they affect photographic plates, or they affect photographic films. Now, what do we mean here? When you go in a hospital and they scan you, or they take an X-ray scan, there is always that photograph that is interpreted by the medics. So that is as a result of this rise or radiations, which will affect the photographic plate, and they can now internally study the bone fracture and all that. So that is one. Two, they are positively charged. They are positively charged. They are positively charged. They have a positive charge. And if they have a positive charge, then this means it can also give us other properties. They ionize gases where they pass. They ionize gases. We are yet to look at what ionization means. So they ionize gases, and also they are deflected. They are deflected by electric fields. Now, if you have an electric field is just a field that has a negative plate and a positive plate. So if we have a negative plate here, this is our plate, this is our electric field, this plate here is positively charged, and then this down plate here is negatively charged. So this is our electric field here, this is the field. Now we have a radioactive sample here. This is our radioactive sample. It is already jealously guarded. Why? Because these radiations are very dangerous. It is like when those stray X-rays reach on someone's body, that's why there are high chances of causing gene mutations. So you are not encouraged to so many times visit the X-ray machine, because they have also side effects. So we have to guard it. So this is maybe a lead gown, or a lead tin, lead metal, lead tin here. Why do we use lead and not any other metal? Because lead absorbs all these radiations. Lead does not allow. So when you go in the hospital, you see medics putting on those lead gowns, not any cloth. So they put in those lead gowns because lead absorbs all these radiations. So if we have this radioactive source here and it emits some particles in which beta or in which alpha is among, but beta is positively charged. From the simple physics of senior 2 of electrostatics, you looked at like charges repel and unlike attract. So if this is our radioactive source and an alpha particle has been emitted here and it is directed to pass through this electric field, one of the properties of an alpha particle is they are positively charged. And so if it is positively charged, from the simple physics of electrostatics, it is obviously that this positive charge will now be attracted to the negative plate. So it will deflect. Deflection is like to bend like that. So it will just bend towards the negative plate. Why? This alpha particle itself is positively charged, and so when it is made to pass through this electric field, it will be deflected towards the negative plate. So that's why we said that they are deflected by electric field. Thank you for listening. The deflection, you'll learn it in the next video. Got it.